I was a mentee in the Chippy mentorship program this year in the spring, and I had a problem that I couldn't figure out how to solve, and I realized that I was going to need to learn a programming language to solve it, and I was new to programming. And I discovered Chippy and came to my first meeting on January 12th, which out of pure luck ended up being the day that the last session of mentees gave their presentations. So my introduction to Python was seeing a dozen or so awesome projects, and I left completely inspired. And so I just want to say thanks to everybody who showed projects last time, and also to Chippy for doing this thing. The problem that I was trying to solve, I'm going to explain, but to set it up a little bit, I have to go back in time and talk about some history. So I'm going to spend about 5 minutes at the end talking about my actual project, and about 25 minutes in the front of it talking about some history that I think is relevant to everything that we have in common, which is an interest in computer programming, even though it may seem a little bit like a tangent, but it'll all come together in the end. So I'm going to rewind to 1880, to the invention of the light bulb. Obviously, the light bulb was a huge deal for human beings, but it was a big deal for a reason that most people don't necessarily know about, which was they discovered something in the process of making the light bulb that they almost overlooked, but it ended up completely changing the world. So just to set this up a little, this is when Randolph Street in Chicago still looked like this. We had no cars. There was no electricity distribution. Couldn't plug anything into any outlets because there were no outlets. Public places were illuminated with flames from gas lanterns. The telephone had been invented about 4 years earlier and patented by Alexander Graham Bell, of course. And the first long-distance telephone call had taken place around this time from Cambridge to Boston, Massachusetts, a distance of about 2 miles. So telephones worked, but they didn't work over long distances. And Chicago, with a population of about 500,000 people, had about 3,000 phones. So to make the light bulb a commercially viable product, they had to overcome a whole series of difficult problems. And the two biggest ones were they had to figure out how to make or reliably manufacture light bulb filaments. Filaments are really small and brittle, and the process of making them was very difficult. And so somebody had to figure that out. And they also had an issue with residual gas inside the bulb. So they would try to evacuate the bulb and take all the oxygen out. But inevitably, there would be some oxygen left inside the bulb, and that would be enough to cause the light bulb filament to burn, to actually combust. So we had light bulb life measured in minutes, and it was just not a commercially viable situation. So the issue of the manufacturing of the filaments was solved by a genius named Lewis Howard Latimer. He was actually the son of an escaped slave from Virginia who taught himself drafting and ended up becoming a master draftsman. And he was recruited by a bunch of inventors at the time to do drawings for patent applications. And he was one of those inventors was Alexander Graham Bell. So he ended up drawing all the patent application diagrams for the telephone, because as you can see here, Alexander Graham Bell's drawings were not adequate. So he ended up helping Bell secure the patent with much better drawings. And he was later recruited by Thomas Edison to draw diagrams for his patent applications, and evolved into an inventor in his own right, and ended up inventing a manufacturing process that could reliably make these carbonized bamboo filaments. And so that was the first solution. The only other problem they had left was this issue of the residual gases inside the bulb. And so someone who unfortunately was forgotten by the history books came up with this idea and thought, okay, if we could just start a small controlled fire on the inside of the bulb somehow, then the fire would consume the oxygen that was remaining and then extinguish itself, and then there would be no more air on the inside of the bulb, and the filament wouldn't be able to burn once it started glowing. And so to test this theory, they added a little metal strip in the center here, and they coated it with gunpowder, and they put some electrodes sticking out the bottom. And then when they sealed the bulb out, they put the two wires on a battery, and it caused the gunpowder to flare up and consume the oxygen, and they had a vacuum. So that worked, and the light bulb was finally a commercially feasible product. And so all the first production light bulbs that came out had this plate in the inside, this piece of metal that was like an artifact left over from the manufacturing process, and everybody just supposed to forget about it. So some people figured out along the way that if you hook up the positive terminal from a battery to this plate on the inside while the bulb was glowing, a whole bunch of current would flow. It was just like, zzz, and they'd be like, whoa, what is that? And so if you hook the battery up the other way around to the negative terminal, nothing would happen. And so they thought, okay, what is this? And they were trying to figure it out. They had no idea what it was. And so Edison did what he always did, which was he named it after himself, called it the Edison effect, and he got a patent for it. And then he promptly forgot about it. The light bulb obviously was huge business, and his company, General Electric, went on to build the electrical grid across the United States and sell bulbs and make tons of money. So they didn't care about the Edison effect. But what they had actually discovered is something called thermionic emission. Thermionic emission is this tendency for electrons to boil off the surface of a glowing metal. So if you have a metal that's heated up so hot that it starts to glow, not only does it give off light, but it also gives off a shower of electrons. Normally, electrons are really tightly bound to their atoms, and they're negatively charged, and they hold on. But given enough heat, they will just take off into thin air. And I call it boiling because it really is like a boiling. It's like when the water reaches a certain temperature, and at some point it's just like, I'm out of here. It just drifts off into space. So, but this was not, I picture it as like a sparkler, right? Like a shower of electrons coming off this filament. But this was not well understood at all because atomic theory had not even entered the scientific paradigm, not until 1897. So this is still 17 years prior to the concept of an electron even entering consciousness. This is a schematic representation. So because electrons are negatively charged, naturally they will be attracted to anything that is positively charged. And because Edison's people had put a positive battery terminal on the plate that was inside the bulb, all these electrons that were showering off the filament and just going off into space turned and just like accelerated toward that plate at like the speed of light, basically. So it was this little invisible lightning bolt of current flowing. But they had absolutely no idea what was happening. So anyway, yeah, they patented it in 1884, the Edison effect. Meanwhile, this is a little bit of a tangent, but it'll all come together. In Chicago, a guy named Frank Wakely Gonzalez was a pastor at a church called the Plymouth Congregational Church on the south side on East 50th Street, still there. And Gonzalez was a humanitarian, and he was fervently opposed to discrimination and economic inequality and so on. And he had a bunch of really rich guys in his congregation, including George Pullman, the notorious railroad guy who the Pullman neighborhood is named after. And also this guy, Philip Danforth Armour. Armour was a very wealthy meatpacking guy in Chicago. And he was also a philanthropist. He had donated some money for educational causes a few times prior to that. So Gonzalez was lecturing these guys. And one day in particular, sorry, I'm jumping ahead here. He gave a sermon where he just laid into them. And he just said, you know what I would do if I had $1 million? I would open a school, and it would be open to everyone, regardless of race or socioeconomic background or whatever. And you would be able to learn a technical trade, like in the sciences or technology or architecture or whatever, and pursue the American dream. And so, so he just laid into them, and Danforth or Armour was sitting in the crowd. He's thinking, And so, as legend has it, 24 hours later, he said, all right, I'll make you a deal. If you dedicate 5 years of your life to running this school, I'll write you a check for $1 million. This is 1893, so $1 million is worth about $40 million by today's standards. So he wrote the check, and they built a beautiful red brick campus on the south side of Chicago, and it was called the Armory Institute of Technology, which you may recognize as the Illinois Institute of Technology, which still teaches the same stuff, architecture, sciences, the whole thing. And because they were flush with cash, they were able to recruit a whole bunch of really smart people from around the country to come and teach and to do work there. And one of the guys they recruited was a guy named Lee of the Forest. Lee DeForest was trying to figure out radio. So at the time, there was no such thing as radio. Actually, we had something called spark gap transmission, which was they realized that if you make an electrical arc, zzz, it sends out a bunch of radio frequency noise into the atmosphere. And so that can be detected miles away if you have the right equipment. So there was a very crude form of radio where they could make these arcs and send pulses, and someone on a ship a few miles away could decode these with a receiver, and you could send Morse code kind of messages through. And so they knew that it was possible somehow to encode sound or some other type of information and transmit it, but they had no idea how to do it because there was no such thing as amplification. So they just couldn't figure it out. But there were a lot of people working on it, including this guy Lee of the Forest. Okay, so fast forward a few years, and this is, of course, 24 years after the Edison effect had been discovered. This guy, John Ambrose Fleming, who was a British physicist, was looking over Edison's patents, and he came across the Edison effect, and he thought, I wonder what that is. And he ended up creating some devices and recreating the Edison effect. And he studied it exhaustively. And basically what he discovered is that it was what is now known as a diode, which is a very simple but very fundamentally important electrical component. It's like a one-way street for electricity. So electricity can flow one way, but it cannot flow the other. Every iPhone and laptop or whatever in this room has diodes in it. I mean, it's an extremely important component. But in 1904, no one cared. There was no such thing as electronics, so who needed a diode? But he was a really good scientist and mathematician, and he ended up figuring out all the properties of the diode and laying really important work for later. So yeah, the Fleming valve is what he called it. He called it a valve. Okay, so back in Chicago, Lee of the Forest, here he is. He was teaching at IIT, or at the Armory Institute, and he was experimenting with these Fleming valves and seeing what he could do with them. And he thought, okay, we know there's a current that's flowing from the filament, from this light bulb filament, to this plate. It's just going through in this glass bulb. There must be a way to control this current somehow. And so he was experimenting with a few different things, and he decided to take this little wire and he bent it back and forth into this zigzag shape, and he called it a grid because it resembled a gridiron. And he put it in between the two elements. And so when the current was flowing, he would put different voltages on this grid and see if he could maybe increase or decrease the amount of current flowing between these two elements. And this worked. So he could like turn the voltage up on the grid and more current would flow. He could turn it down and less would flow. He could go up and down and up and down and up and down, and it would follow. And so he realized that there was a very strong current that was basically following anything he did on the grid. So he could tweak the grid voltage by any amount he wanted, and this very strong current would mirror exactly that. And that's basically what amplification is. So you can take a very weak signal, for example, like from a telephone, and put it on the grid. It'll wiggle up and down, and this more powerful current will follow it exactly. And so this absolutely changed the world. I mean, the things that this led to are insane. But actually, he did a very poor job of building these samples. He actually he did get a patent for it, and it says a device for amplifying feeble electrical currents. But he couldn't explain it. And I mean, he could explain it in general terms, but he couldn't explain it mathematically. And so a lot of other people challenged him on his patent and ended up getting embroiled in a huge legal mess. And he was forced to sell the patent just to pay his legal bills. And he did manage to make a few of them, but his workmanship was not the greatest. And so his tubes were very inconsistent, and it was just seen as sort of a flop. So just for perspective, 1908, Ford Model T comes out. This is a point in time where humans are about to change the way they live very drastically, very quickly. So the next year, a student at Columbia University in New York, got his hands on one of these tubes that Lee DeForest had made and studied it very thoroughly and ended up figuring out all the mathematics behind it and doing all the work that Lee DeForest probably should have done. And he published an article in an academic journal, and it just blew up. All of a sudden, everybody, all these inventors, were making these funny glass bottles with these elements on the inside to figure out what this thing was. So they all knew there was something there worth investigating. but they couldn't figure it out. So by 1912, General Electric, which had been selling light bulbs now for 32 years and making ridiculous amounts of money, was a huge company. And they acquired the patent and hired a whole bunch of really smart guys, including this guy Irving Langmuir, who went on to win a Nobel Prize later for other work. And they just really tore into this thing. And they did thousands of experiments, and they figured out that it's all about the materials and the geometry of the elements and the proximity of the different elements to each other and the surface area and so on. And they managed to finally introduce the first amplifying triode. They called it a triode because there's 3 elements. We had the diode before with the 2. So they called it the pleiotron. Pleio is Greek for gain or for more. So you put in your weak signal, you get more signal out of it. And yeah, this thing completely changed the world. So by 1915, long-distance telephone communication was solved because of the triode. They could just amplify the signal as many times as they needed to across the country. And in 1915, Woodrow Wilson and Alexander Graham Bell ceremoniously made the first transcontinental long-distance telephone call from New York to San Francisco. Also in 1915, the radio receiver became a possibility because of the triode. So suddenly we could pick up these very weak radio waves from the atmosphere and amplify them enough to drive a speaker and sit and listen to the radio. So we had radio transmission and receiving because of the triode. By 1920, we had the public address system because of the triode again. This totally changed the nature of politics because prior to the PA, you had to have a very loud, thundering voice to be heard and get your message across. But with the PA, all of a sudden, anybody could be heard. By 1925, we had the first musical recordings. This thing here at the bottom is basically a carbon button microphone from a telephone, the mouthpiece, mounted on a stand and plugged into a triode vacuum tube and amplified. So music recording was suddenly a thing. By 1929, this guy by the name of Philo T. Farnsworth finally realized his vision of inventing the television. So he was actually an 11-year-old boy plowing his family's farm in North Dakota when it suddenly dawned on him that this back and forth motion of plowing row by row, if viewed from the sky, would be sort of like he was drawing a picture. And he realized that could be a way to break pictures down into a series of lines and then send them as a series of data and then reconstruct a picture at the other end. And so using triode vacuum tubes, he was successfully able to do this after many years of effort, and eventually he won the patent. He was disputed by one of RCA's inventors, but he ended up winning in the end. 1935, radar was invented as a result of the triode tube, and of course that totally changed the nature of warfare. Although I'm bummed that they didn't keep pursuing the old-fashioned way of listening for airplanes. Ear binoculars. By 1942, a professor by the name of Atanasoff and his graduate student, Barry, realized that you could use vacuum tubes to do computation, basically to make a digital computer. So digital computation, the theory behind it had already been developed, and we had mechanical digital computers with wheels and pulleys and all kinds of stuff. But they were obviously very limited. And he built, it was interesting, he was driving from Chicago to Rock Island, Illinois in the middle of the night, and he suddenly dawned on him that a tube could be used for this. And he ended up pulling his car over and making a whole bunch of notes. And then he kept driving, and then he thought of another thing. He's like, oh, and then we could do this. And he pulled his car over. And this trip took all night long because he kept pulling over and making these notes. But his notes were convincing enough and his ideas were solid that he got funding to try and build this computer, and he built it, and it's the first electronic digital computer with 300 tubes in it. And it was capable of solving complex physics equations, so it was a huge deal. And within a couple of years, in the United Kingdom, they took the same idea and scaled it up and built a computer with 1,500 tubes, and called the Colossus. And this was used to crack German ciphers during World War II. And then in 1946, the ENIAC came online. And this was actually intended for the war effort, but didn't make it in time. This thing was a complete beast. It had 18,000 triode tubes in it. I mean, just a total nightmare to maintain. And an average of like 1 tube failure per day. So they had to be like, okay, which one? But it was 1,000 times faster than anything previously ever built. And they used it to calculate missile trajectories, basically, to do differential equations. But one really interesting thing about this computer is that there was a pool of, to program the computer, they hired 6 engineers. And the engineers came from an electrical engineering school where there were about 100 enrollees. And they picked the 6 best enrollee or students from the whole school. And they were these mathematicians. And of course, there were no programming languages at the time. So to program these systems, it was just like a gigantic bank of logic circuits. And they had to basically figure out how to break the problem down that they wanted to solve into logical steps, and then patch these logical things, circuits together to build a system that could solve that problem. So everything had to be programmed physically with patch cables and switches and so on. Programming was ridiculously complicated. And the amazing thing about it is that all the programmers, all 6 of them, were women. And this was entirely forgotten about by the computer industry until only a few years ago, when a woman by the name of Kathy Kleiman, who was a graduate student at Harvard studying computer science, realized that this was a part of history that had been completely overlooked. And so she did a documentary on these women, and some of them have passed away, but some of them are still alive. And they've all since won some awards and so on for their early work, but super important work. So a few years later, after the ENIAC, it was scaled up again to the EDVAC computer, and then we had the BINAC and the Scisrac and the SEAC and the MANIAC, literally. So things were getting totally ridiculous, and this concept they couldn't just keep scaling this thing up like crazy. So there was a lot of pressure on how do you miniaturize this electronics. And so, oh yeah, this one was a total monster, 60,000 tubes. I mean, what? That's insane. What? Yeah, it consumed enormous amounts of electricity. So you can see they made progress. These are functionally equivalent modules. So they were making progress reducing the size of these things over time, but there's only so small you can get with a glass bottle. So they knew they had to figure out a way to achieve something like thermionic emission with some other kind of material. Well, as it turns out, in 1926, a German inventor by the name of Lilienfeld had discovered that if you take this metal oxides, basically rust, and you contaminate it with some dopants, you can create some really bizarre materials, some materials that have very strange electrical properties. So, for example, you can make a material that in one state acts like an insulator, so it does not conduct any electricity. But then if you bring an electrical charge near it, all of a sudden it turns into a conductor. Totally weird. So this is what the semiconductor is. It's a material that can act as in 2 different states and can be changed. So he patented this, and he invented basically the field effect transistor. And again, a FET is ubiquitous in electronics everywhere. Phones, everything has FETs in them. They're incredibly important. But in 1926, the companies that were making the vacuum tubes had grown to be huge economic powerhouses, and they didn't like this. They saw this as a threat, and they basically squashed it. They managed to buy out his patent from him or wrestle it away from him. And he ended up retiring depressed in the Caribbean, although maybe he was happy in the Caribbean. Anyway, so it was squashed and forgotten about for 20 more years until these shysters managed to figure it out. They unearthed it and saw it and were like, ooh, maybe this is useful. And they investigated it, and they recreated the transistor. So they got a working transistor, and they tried to patent it, and they were denied because it had already been patented. And so they had to jump through a bunch of hoops to get around the original patent, and they successfully got around the patent and ended up winning the Nobel Prize for inventing the transistor, which is... Anyway, so you can see this enormous improvement, this tiny little can that contains this device that does the same thing as a vacuum tube. But it's already a little absurd. I mean, you can see the transistor itself is just this little bit here. So just to give it a container to live in, the container is already so much bigger than the transistor. But it was seen as a huge improvement, and they were so small already that it would start to get unmanageable if they were any smaller. So they released them that way. And of course, if you build an ENIAC style computer with 18,000 of these, it would be significantly smaller. And in 1953, the University of Manchester built the first transistor-based computer called Transistor Computer with 200 transistors. And this thing is about this big. So gigantic improvement. Of course, only 200 transistors, so a lot less powerful, but still demonstrated that transistors could be used to make digital computers. So by 1958, this guy, Jack Kilby, who was a new recruit to Texas Instruments, who was also making semiconductors, he didn't have any vacation time accrued because he was a brand new employee. And so when everybody left for summer vacation, he was forced staying behind and working. But he had gotten permission from his bosses to tinker around and do some experiments. And he had some really good ideas. He had realized that, okay, hold on a second. If we can fit 2 transistors in one package, then to build an ENIAC computer, we'd only need 9,000 components. Or if we could fit 4 inside, we'd only need 4,500. And actually, if we could fit 4, then we could pre-wire them together into different circuits. Normally, transistors were used discretely as a component in a circuit that also had resistors and capacitors and so on to make a functional block. But he realized, well, if you could scale that up and make a functional block inside the package itself and give that to the electronics designer, then it would greatly simplify the design process. And so he did some experiments and successfully made a multi-transistor device on a single piece of germanium substrate. This was commercialized right away, and they started selling these things to the Army. And as far as I'm concerned, this is like the birthday of Moore's Law. Because the obvious question is, well, if we could fit 4, can we do 8? You know, can we do 16? Yes. So, the sky's the limit. So 1959, the planar process was developed, and this greatly increased the reliability and made manufacturing transistors a lot easier. And so this sort of made it possible to scale things much more easily. And by 64, we had 120 transistors on a single substrate. So this was a huge deal. The next year is when Gordon Moore made his famous prediction that we were going to be able to double the number of transistors about every 2 years. Or I think he said about every year and a half at first, and that was corrected to about every 2 years. And if you look ahead to 1971, just from 65 to 71, doubling 120 that many times in a row brings you to about 2,300. So they came out, they were cramming 2,300 transistors on a single chip and pre-wiring them into different functional systems, memory and numerical processors and so on. And they made basically the first CPU, the first central processing unit. So I'm not going to go through everything else. I'm just going to skip to 2017 where we have the 14 nanometer process, which is yielding about 20 billion transistors, which is insane. And the 7 nanometer process is already tooled up and running. And in 2018, we're going to see chips with about 40 billion transistors. So back to this little glass bottle here. When it comes to the thing that we all have in common in here, which is this interest in computer programming or digital computers, this thing is really the beginning of the road. This is where it all started. And I find that to be kind of amazing. An accidental discovery of a weird phenomenon turned into all this, which is crazy. But another thing about these glass bottles that is really amazing is that they also make beautiful sounding musical amplifiers. So they lend themselves really well to making great sounding amps, which is why if you know a guitar player, they probably have a tube amp. And I won't get into it. There are lots of physics reasons as to why they happen to be great at amplifying musical waveforms. One of the things is that they tend to distort musically. So they will distort in octaves. And octaves always work with music because it's the same tone. And so if it adds in some tonal distortion, it happens in a way that rhymes with everything else tonally. So it's like it tends to make things sound rich. It's sort of like a 12-string guitar, how a 12-string guitar sounds really rich because there are octaves. Tubes naturally do that to music. So it's one of the interesting things about them. And this leads me finally to what my problem was, which is, so I have this business here in Westtown called Elektronaut. I'm the Elektronaut. And I design and build audio equipment for professional musicians and recording studios. And I use all vacuum tubes. So you can still get vacuum tubes. They're still made in Russia and Slovakia and China. and they're excellent. And some quick examples of my work. This is a microphone preamplifier that I make, and you can see the little glass bottles in there if you look carefully. This is another product I make. It's a compressor, and you can see it's quite a bit more complex. It's got 14 tubes in it. So the problem that I had has to do with this group of 8 tubes right here. Tubes aren't all exactly the same. They differ from one to the next, even of the same type. And that can sometimes be very problematic. So it's sort of like if you were to buy a pack of 9-volt batteries and take them home and measure the voltages. One might be 9.1, and another one might be 8.9, and you measured them all up and graphed them, it would probably, the distribution would look somewhat Gaussian, right? It would be like most of them are 9, some of them are a little high, a little low, and there's some outliers maybe. So tubes are the exact same way. And in this particular design, the circuit really, in order to get the best performance out of it, the tubes have to match as closely as possible. So it doesn't matter if they're a little high or a little low, it just matters that they're all exactly the same. And so this was really challenging to me because, and another thing is the tubes can't just match in one position, they have to match across a whole range of values. So I made a little machine to automate the measurement process, and I could just plug in a tube and hit a button, and about a minute later a text file is written to my computer that contains some numbers. So you can see a row or a column of voltages on the left side, and then the resulting column of currents on the right side. So the voltages are always the same, and the currents are always a little different. And I need to go through and measure. I have 1,200 tubes in my lab that I have to measure. It's a total nightmare, right? And then I have to somehow produce 1,200 text files and then figure out which tubes are matches with the other ones. So this was my problem, and I had no idea how to do this. And so just as an example, if I were to plot that tube data, it would look like this. So an ideal match would obviously have the exact same curve. An example of 200 tubes looks like that. So they're a little bit all over the place. And there's one data point just showing a distribution of a single voltage for all the tubes. So the software that I wrote in Python does this, and it does it really well, and I'm super excited about it. I actually had to rewrite the spec sheet in the manual for my compressor because all my figures are better than they were when I originally released the product. So this is, some of my clients will buy 2 compressors, and then they want them to both match exactly. And so not only do I need to match 8 tubes, I have to match 16, which gets even more difficult. But here's an example of 16 tubes that match perfectly from my little Python program. So I'm super happy about how it all turned out. And I just want to say that when I started, I thought I was like, okay, I'm going to make this application, and it's going to have like a GUI and buttons. And I spent all this time like sketching it out, and I thought it was going to be really cool. And then I discovered Jupyter, and I was like, so Jupyter totally rules, as everybody knows. So the way this works is it basically, I'm not going to get into the nitty-gritty details or whatever, but there's a module that will I have to paste in a path to where this folder that contains all these text files is. And then the first import statement here will just run this module that brings in every single text file, cleans up the data, and builds a big data frame. So that works. And that's this data frame here. And then, okay, I use the describe statement or method to give me my stats on the data frame. This is a step that some functions that I made to make that graph that shows all the tubes together. This distribution one, and then this monster here. So this calculates basically the difference between every data point or every tube's data points from every other tube's data points. So it builds a humongous data frame. It's basically the square of the number of tubes, and then it goes through a bunch of sorting methods to basically figure out, okay, well, what are the closest ones? So it uses least squares. So it basically figures out the square of the difference between every data point and then totals them up and gives it a score at the end. And so the lower the number, the better. So a perfect match would have a 0 score. And so if I show you this, I'm not going to run this because it actually takes, you can see, 63.22 seconds to calculate 1.3 million values, resulting in 82,000 rows in my data frame. So you can see how there's this column here called error sum, and it just produces a score for each tube as it relates to every other tube. And then that can be, there's a function here in case I have a tube like, oh, I've got tube number 245. I need a match for that. So I can enter 245 and it'll say the best match is this or that or whatever. How many do you need? And then this one I can actually run because it's a little faster. Builds a data frame for all the best matched sets in the entire batch. There's only 200 tubes in this data set right now. But if I run it, it'll ask me, well, how many do you want? So I can either say 8 if I'm building 1 unit, or I can say 16 if I'm building 2. So I'll just say, well, I'll say 16. And then goes through and it says, okay, the best set is this one here. It's got a score of 13.92. The second best set, the third best set, blah, 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 blah. So it tells me what all the sets are. And then if I go down to the bottom of the list, I can say, well, show me a plot of the best set. And then it makes this little plot here. So that's the first 16 tubes, the best 16 of the batch. So this is my project. It was it so greatly made my job easier, and I totally fell in love with Python in the process. So so thanks to Chippy for helping me figure this out.